All right. So where we left off yesterday was we started to do confidence interval questions, where we introduced really four separate formulas. We've really only made use of two of those formulas so far. The only problems that we've done so far is where we've had large sample sizes. We've done large sample sizes where we both know sigma and where we don't know sigma, so where we know the population standard deviation and where we don't. And then today what we're going to start to use as well is the formulas that we covered yesterday for small sample sizes. Right? We'll see that one of those formulas that we're going to use today is really similar to the ones that we used last class. But there's also going to be one of them where it's a little bit different, specifically where we start using t-values in our equation instead of using z-values. And what is going to be the only scenario where we use t-values in our confidence interval formulas? When sample size is less than 30 and...
It's not a population.
And we don't know the population standard deviation. We don't know sigma, right? So whenever we don't know sigma and we have a small sample size, that's when we're going to use t in our confidence interval question. All right. So that's pretty much where we left off then. Then let's start up here today. Just jump right into this example question right here. So it's more confidence interval questions for the population mean, and it says a sample of size 15 is drawn from a normally distributed population and it has a sample mean of 35 and a sample standard deviation of 14. Construct a 95% confidence interval for the population mean and interpret your results. All right, so just like we've always been doing, how do we know that this is a Chapter 7 question? Because it says confidence interval. Good. Here it's because it says that we're trying to construct a confidence interval. Whenever we're doing confidence intervals, then we're going to be in Chapter 7. And whenever we're doing confidence interval questions, how do we always start these off? What's our first step? Good. So the first question we're asking ourselves is, n our sample size greater than or equal to 30? And then the second question that we ask ourselves is sigma known? So let me ask you this. Is little n greater than or equal to 30? I heard both answers. No, it's not. Why is it not? Good. Little n stands for our sample size. Here our sample size is 15. So we're going to answer no to this question. Do we know sigma? No. We do not know sigma. Again, sigma stands for our population standard deviation. But here it tells us that this is our sample standard deviation. So we don't know our population standard deviation sigma. So again, this answer is no. We've answered no to both questions, so therefore we're going to use t-values. Awesome. So the only time that we ever use t-values is whenever we're answering no to both of those questions right here. All right. So that means then the formula that we're going to use for our confidence interval is going to be x bar, since that's still going to be our estimate for the population mean, plus or minus, now we're going to use t sub alpha divided by 2 times, we always are going to have the square root of n down here in the denominator, but what are we going to put up in the numerator for the symbol? S, because we don't know sigma, so we're going to use our sample standard deviation instead. Again, in case you don't remember this formula, we go to our formula sheet. Just to point this out one more time for today, we're up here in this region right here of our formula sheet. We said that we had a sample size less than 30, so we're going to be down here. And we don't know sigma, so sigma is unknown, so we're using this formula right here. Everybody good with how to find the formula on your formula sheet? All right, so now we have this formula right here. We can start plugging stuff in here. In this problem, x bar is equal to what? 35. Then plus or minus, we'll skip t here for a second. We already said that our sample standard deviation was equal to 14, and you already told me that our sample size is 15, so we're going to have the square root of 15 right here. Everybody good with this example so far? then the only thing that we're still missing is our t value, right? So real quick, if we go back to our formula sheet again, one of the things that's different, right, and especially if you look at the notes, the only thing that's not included in the table in our notes is that column right here, so I'll kind of cover it up. But if you look for all of these things, one of the things that we have over here that we don't have for the first three formulas is this little n minus 1. Right? So the bottom right-hand side over here, we have little n minus 1, which stands for we have little n minus 1 degrees of freedom. So the first thing that we're going to have to do is we're going to need to know how many degrees of freedom that we have whenever we look up our t values. Right? This is going to be something that we haven't done before. So if our degrees of freedom is equal to little n minus 1, then how many degrees of freedom do we have in this example? How many? 14. Good. 14. Because our sample size is 15. 15 minus 1 is 14. All right. So now let's try to figure out how we look up our t value. So for that, we need the table that I just got done handing out. So let's take a look at this table here for a second. It's the one that's all the way in the back that I just handed out. All right, so here's this table, right? First off, just like we had before for our z table, here we know that this is our t table because right here it says a t. We also have a front side to this table and a back side to this table. If you look right up here, the top left-hand side where it starts with a 1, that's what I'm going to start calling the front side. And if you go here to the back page where it starts at 51, this is what I'm going to call the back side. So let's go over here to the front side. We just found out how many degrees of freedom that we have. And we just found out how many degrees of freedom do we have? 14. So we're going to come down here to where it says 14, and we're going to be looking at this row right here where it says we have 14 degrees of freedom. Then the only other thing that we still need to figure out is what column that we're in, and then we're going to have identified our t values. So let me take a step back here for a second. One of the main differences between this table right here and your z table is these numbers now that are in the body of your table, these are not percentages. These are now your t values, right? So these things in here, all these values in here, those are all your t values. That's usually a source of confusion whenever people are using both tables, because on the z table, the middle portion is percentages, but here in the t table, the middle portion are your t values, right? Is everybody good with that the middle thing right here is t values? All right. So we know that we're going to be right here in 14 degrees of freedom. We just need to figure out what column that we're in order to figure out our t value. So let's come up here to the top. We have these little subscripts on our t's in that very, very, very first row. The subscript on our t's are going to be the t sub alpha divided by 2's that we're working with. Right, is everybody good with this? We know what these alpha divided by 2 things are, right? How did we get alpha? Good. It's 1 minus our confidence level, right? So we know that our confidence level, which I'm still abbreviating by CL, is given to us by 1 minus alpha. So in this problem, the one that we're currently working on, what is our confidence level? 95, so it's equal to 0.95. So therefore, alpha is equal to what? 0.05. And therefore, alpha divided by 2 is 0.025. So what column do you think? Oops, alpha divided by 2 is 0.025. So what column do you think we're going to go to? The fourth one. This one right here, right? The one that has a subscript of 0.025. Everybody good with how we got to that column? All right. So now if we match up these two things, we see that our t value is 2.145. Everybody good with how to get that t value? All right. Well, now we know our t value. We can drop 2.145 in right here, and now it's just an arithmetic exercise. So really the main difference that we have here in this problem primarily just deals with the fact that we answered no to both question, so therefore we're going to use a t-value. And now how we're looking at that t-value is also a bit different since we're using a different table. Whenever we want to look up a t-value, we need to know both our degrees of freedom and what our alpha divided by 2 is. And we said that our alpha divided by 2 is 0.025. So once we match up those two things, that's how we got 2.145. All right, if you do this arithmetic, you're going to come up with the interval of 27.2 to 42.8. Any questions about how to get those numbers? All right, then the last thing... it really just depends on the answer choices that you're given, right? Usually, because they're always just going to be multiple choice stuff, usually if you carry one decimal place, you're going to be good to go. There's never going to really be answer choices that are so close that you need to carry 2 decimal places for. Question? You good to go? Yep. Any other questions? Everybody good with this? Then the last thing that we need to do is what? Interpret our results. And what's our interpretation going to be? Awesome. Yep. Always do population, because we're always just trying to estimate something from the population. We're never trying to estimate something from the sample because we have our sample, so we can calculate out stuff from our sample. So I know I scribbled here, but it says we are 95% confident that the population mean mu is in the interval 27.2 to 42.8. Right? And again, just to reiterate what I said yesterday, the only thing that you're ever really going to need to change from this interpretation are what I just put in boxes. Obviously, our confidence level could change just depending on the setup of our problem. We're either going to be looking at the mean mu, or what else could we be looking at in this class? The population proportion P, right? So we're either going to have here mean mu or proportion P, and then obviously just depending on our numbers, we're going to calculate out different intervals. All right, any questions about number 1?
For the exam,
yep.
For the multiple choice, will there be like the interval and like the interpretation with the interval as the answer, or will it just be like?
Great question. You're never going to have to do it on the exam for the multiple choice. However, there is going to be a written section on your guys' final exam portion of it. It's something that the department requires, that we don't just do multiple choice, but that there's also a written section. And on the written section, if you ever have to provide an interpretation, this would be the interpretation. That's why throughout the semester, all the examples that we do in class are always written questions. But then that should prepare you sufficiently for that final exam portion. But we'll talk more about that final exam portion once we get there. Any other questions about number 1? Then let's go on to number 2. Take maybe 4 or 5 minutes or so for yourself and see if you can answer number 2 by yourself. Does anybody need a little extra time? Alright, then let's do this one together. A sample of size 19 drawn from a normally distributed population has a sample mean of 43 and a population standard deviation of 12. Construct an 80% confidence interval for the population mean and interpret your results. So again, how do we know that this is a Chapter 7 question? It says confidence interval. Whenever we're doing confidence interval questions, how do we always start? And if we know sigma. Awesome. So here in this example, is our sample size greater than or equal to 30? No. Do we know sigma? So what does sigma stand for? Our population standard deviation. Does it say we know our population standard deviation? Yes. It does, right? Here it says we have a population standard deviation of 12. So we answered no to one of them and yes to one of them. What do we use? Z values, right? When's the only time that we use T values? If we say no to both of them, right? Like if we have a sample standard deviation and if we have a sample size that's less than 30. So we're going to be using Z values. And is everybody good with why we're using Z values? All right. So we're going to be using Z values. So therefore what we're going to have is we're going to have our sample mean, which is going to be our statistic, plus or minus. Now we have Z sub alpha divided by 2. And down here in the denominator, we always have the square root of n. What symbol are we going to use in our numerator? Sigma. Whenever we know sigma, we use sigma. So we're going to have sigma up here. So now we can start plugging values in here. What's x bar in this problem? We'll skip z here for a second. We already said that sigma was 12. And what's our sample size? 19. Everybody good with this so far? So what we're really doing here is just a problem that's really similar to the ones that we did yesterday. Right? We need to know what z sub alpha divided by 2 is. So let's just go over that in terms of pictures, just in case anybody missed yesterday's lecture. Well, we said that since we're using z values, we know that we're going to be using a normal distribution. Then we're going to have two cutoffs whenever we're doing confidence intervals. And in between these two cutoffs, we're always going to put our confidence level. Here our confidence level is 80%. So therefore, since we have 80% right here, and it's a symmetric distribution, we know that over here we're going to have 10% or 0.1, and over here we're going to have 10% or 0.1. What we're trying to find out are what are these z values right here, and we're calling these z values z sub alpha divided by 2. Now, where does this alpha divided by 2 come from? We know that our confidence level, right, which I'm abbreviating as CL, confidence level, is given by a formula of 1 minus alpha. 1 minus alpha. Well, if our confidence level is equal to 80%, if you solve for alpha, then alpha is going to give us 20% or 0.2. So therefore, we know if alpha is equal to 20%, and we're putting 10% right here and 10% right here, then over here, this is the same thing as alpha divided by 2. So that's why we're calling these z values z sub alpha divided by 2. Right? Is that jogging everybody's memory about our discussion yesterday? So if we're trying to find a z value for alpha divided by 2, then essentially what we're trying to find is a z value that corresponds to 10%. If you look up the z value that corresponds to 10%, what z value do you get? 1.28. Again, it should be negative 1.28, but you're exactly right, because what we said was is here we're going to add and subtract this anyways, so it doesn't matter if we're calling this 1.28 or negative 1.28, it's still going to be the exact same thing. Alright, is everybody good with how to get 1.28? Alright, we're going to pause here for a second, because I want to take you guys back to our table. If you go back to our table, you're saying, well, why are we going to the table? The table only uses t values, and we're not using a t value here, so why are we going to the table? Well, let's start off with this. In this problem, we have an alpha divided by 2 of 10%. So So therefore, what column is 10% going to be?
5. Wait, no, it's not. 2. Column 2.
The second column, this column right here. Right, is everybody good that it's that column? Here, we're looking for 10%. 10% can be written as 0.1. So if we're looking for an alpha divided by 2 for 10%, then we're going to use the second column. All right, is everybody good with this? Now, what I said was is that all these things right here, these are all what?
T values.
These are our t values, right? Like that's the important distinction between our z table and our t table. These things right here, these are all of our t values. Now, we also know this though. When does our t distribution start to look like the normal distribution? Talked about this yesterday. Good. Once it's above 30, right? Once our sample size gets to be 30 or greater, there our t distributions are pretty much exactly like our normal distributions, right? And we know that from what? The brewer, right? The brewer figured that out, but specifically we know that from the central limit there, right? And I'll get your question here in just a second. So here's the thing though, right? We say that the t distributions get really, 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 really super close to the normal distribution once we're at a sample size of 30 or higher. Technically speaking, they're not exactly the same, but they're super darn close that it's good enough for us, right? We technically need to have a sample size of infinity. That's when our t distribution is exactly equal to our normal distribution. Right? Is everybody good with that? That we keep getting closer and closer and closer, but technically for them to be equal, our sample size needs to be at infinity. So what we have here, we know that the way that we calculate out degrees of freedom is what? So far, that if you wanted to calculate out your degrees of freedom, little n minus 1, right? So here what this is then essentially saying is that as we go up in degrees of freedom, we're also going up in our sample size. Right? Does that make sense? So now if we keep going up in our sample size, if you go all the way to the back side of this table, our degrees of freedom keeps going up, which means that our sample size keeps going up. But now if you come all the way down to the bottom, how big has our sample size gotten? It goes all the way up to infinity, right? So it says, hey, it goes to like a sample size. If we're at 100 degrees of freedom, what is your sample size? 101, right? So here we stop at a sample size of 101, and then we make this huge jump, and we say, hey, what happens if we had an infinite sample size? Well, right there in the brackets right next to that, what letter do you see? C. So it says, hey, once you go to an infinite sample size, now what it's going to be, it's not, technically it's no longer a t value, but now we're at a z value. Right? Does everybody know why we're at a z value? So what is that saying? It says that this very last row right here, since we're at an infinite sample size, this very last row, these are z values. Right, is everybody good with that? So all of these other things in here in this table, these are all t values, except for when we have an infinite sample size, then this last row right here is z values. So I already asked you what column we were in for an alpha divided by 2 of 10%, and you said that we needed to be in the second column. So now if we follow the second column all the way down to the bottom, what z value do we have? 1.282, right? So now what is that saying? We can get z values to the third decimal place using this table, right? From our other table that we used, we said it was going to be 1.28 because that was the number that was closest. But now we can go down to 3 decimal places. So we obviously don't have all of the z values here, right? Here we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 z values. And we have a whole bunch of z values on our other page, on our other table, right? Technically there's like 799 of them, right? Here we only have 9 of them. So for very, very few z values, but these are also very common z values, we can find out what that z value is to 3 decimal places, right? And this is how the answer choices are going to be made for these types of problems now that you guys are familiar with this table. So with that, I mean that from now on, if you have to find a z value and the z value is given on your t table, the answer choices are going to be made using those 3 decimal places, not just 2 decimal places. Now again, even if you just use 1.28 right here, you would get something very slightly different than if you used 1.282. Those 2 answer choices are never going to be given to you at the same time, right? Meaning that you're never going to get one answer choice that says 1.28 and then another answer choice that's using 1.282. The answer choices are never going to be that close. But one of the things to keep in mind is if you're only using 1.28, chances are you might come up with something that's very, very, very slightly different than the answer choices on the test.
I think that happened to me on the Ross exam because I forgot to pretty much like on one decimal point. So.
And it happens very, 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 very rarely, right?
Yeah.
The only time that would ever really happen is if this was big enough to make sure that if you multiplied it by a 2, that the rounding error would put you up to the next decimal place, right? So it's very, very rare, but you're right. At most, it probably is just going to affect the second decimal place. All right, everybody good with this? Any other questions? Josh, I know you had your hand up earlier.
Yeah, you kind of answered it as far as the infinity line, but anything from 31 to, or from 30 to 100, is there ever a use for those t-values?
Great question, right? So Josh is asking this. He says, well, if we have a sample size that's 30 or greater, then by necessity, we're going to have degrees of freedom that are 29 and above, right? So once we get to a degree of freedom of 29 and above, doesn't the central limit theorem kick in here anyways, and why do we even have these t-values? Completely reasonable question, right? The thing is this. You're correct if we only take one sample. What we start to do in chapter 9 is we say, hey, suppose we didn't just take one sample, suppose we take 2 samples, right? Now, if one of those samples, or both of those samples, have less than 30 in it, now the central limit theorem isn't going to kick in for that sample. But since we're going to be considering these samples together, we want to make sure that either the central limit theorem applies or it doesn't apply. So if the central limit theorem doesn't apply for one of those samples, now we're going to be using t-values forever. Right? Does that make sense? So an example of that might be this. Suppose, and we'll get to this a little bit in chapter 9, but suppose that somebody comes up and says, hey, I need to draw some blood from you, and I need to do some kind of test. So then they draw blood from you, they turn around, they walk away, they break the vials, and they're like, crap, dude, I need to draw a second sample, right? To which you would probably say, no, yep. But suppose they take a second sample, right? And then somebody goes, well, no, we still have a drop of blood right here. Now we have 2 samples that we can work with. And if they wanted to somehow consider something with 2 of those samples. Another scenario might be you come into this class or into any kind of testing environment, you take a test and you ace it, right? And somebody goes, no, that's an impossible score. You must have cheated. I want you to take the test again. Well, now you have 2 samples from the same person. So there's several scenarios in the real world where it would be necessary to take 2 samples. And if for some reason those samples weren't both above 30, we're going to end up in this environment because we're going to start adding sample size 1 to sample size 2. All right. So, but we'll get to that a little bit more in chapter 9 with probably some better examples than I just came up with off the top of my head. All right. Is everybody good with how to get to this point in this problem? All right. Once you do this arithmetic, you're going to end up with 39.47 to 46.53.
Are we just going to switch back between having 2 decimal point and 1 decimal point? Or does it?
I'm being very inconsistent. You're right. again, usually your answer choices on your homework and on your exams are just to 1 decimal point. But the answer choices that you're going to see, so let's say that we rounded this and we made this to 1 decimal point, like this. The answer choices that you're never going to see, like this is never going to be answer choice A, and then answer choice B would be 39.4 and 46.5. You're never going to see answer choices where like the answers are this close, where it's going to matter whether you carry that second decimal place or not. But you're right, I'm being very consistent with how many decimal places I have. Usually you just get away with doing 1 decimal place. Yep. All right, and what's our last thing that we need to do for this problem? Our interpretation. And what's our interpretation?
You're 80% confident that the mean mu is in interval 39.5 places.
Awesome. Awesome. So we are 80% confident that the mean mu is in the interval we just calculated out. Any questions about number 1 or 2? You guys starting to get the gist with these problems? Question?
Why do you switch from brackets to parentheses?
So the brackets and parentheses right here, whether or not these are square or whether they're round, doesn't matter. Why doesn't it matter? It doesn't matter because the variables that we're dealing with, if we're using z values right here, then we're saying that they are coming from our normal distribution. And our normal distribution is we're using it as a continuous random variable. So therefore, we're saying that the variables that we're working with are continuous. And remember that the probability of adding or subtracting just one value of that continuous random variable is just probability of 0, right? So we're just adding and subtracting 0. So technically speaking, we would be as equally as confident for this interval if it was a round bracket or a square bracket. So therefore, since we're just looking at our confidence level, it doesn't matter whether they're square or round.
Okay, thank you.
Yep. Your textbook or the textbook that accompanies this class primarily uses round brackets, but theoretically there's no justification for that. Good question. Any other questions whatsoever? Then let's go on to the next example. Again, take maybe 4 or so minutes for yourself and see if you can answer number 3 by yourself. Does anybody need a little extra time? All right, then let's do this one together. A sample of size 12 students drawn from a large, normally distributed population has a sample mean of 2.71 and a sample standard deviation of 0.51. Construct a 90% confidence interval for the population mean and interpret your results. So again, how do we know that this is a Chapter 7 question? Confidence interval. What's our first step whenever we do a confidence interval question? Awesome. See if our sample size is greater than 30 and if sigma is known. What's our sample size in this problem? 12. So therefore here we're going to answer no. Do we know sigma?
No.
So we only know our sample standard deviation. So we don't know sigma, since sigma is our population standard deviation. So here we're going to answer no to this as well. Is everybody good at saying no to both of these? Then what do we use? T. Awesome. So then we're going to use the formula for our confidence interval of x bar plus or minus t sub alpha divided by 2 times something divided by the square root of n. And what symbol are we using in our numerator? S. Because we don't know sigma. So now we can start plugging in values. Our sample mean is 2.71. We'll skip t here for a second. S is 0.51, and we already said that our sample size is 12. Everybody go with these first three numbers? All right, then if we want to look up a t value, what do we still have to know? We have to know our confidence level and our degrees of freedom. Our degrees of freedom is going to be equal to what? 11. Since it's little n minus 1, we said that little n was 12, so 12 minus 1 is 11. Now we also need to know what alpha divided by 2 is. So let's go through our usual routine. We said that our confidence level for this problem is equal to 90%, which is the same thing as 1 minus alpha. So therefore, alpha is going to be equal to 10%, and alpha divided by 2 is going to be equal to 5%, or 0.05. So therefore, whenever we look up our t values, we're going to go to the column that has the subscript of 0.05, and we're going to follow it down to where we have 11 degrees of freedom. If we do that, what column are we going to be in? The third one. I'm going to try to differentiate it by just saying that right there now. So we're going to be in the third one, and we said that we're going to have 11 degrees of freedom. So where these two things match up, we get 1.796. Everybody good with how to find a t value of 1.796? We plug in 1.796 right here, and then do this arithmetic. We're going to end up with 2.45 to 2.97. And yes, I know I'm doing two decimal places again. Right? Again, it doesn't matter. You can just round to 1 if that's better. Everybody good with these numbers? What's the last thing that we need to do? Our interpretation. What's our interpretation? So I know I'm scribbling, but we're 90% confident that the population mu is in the interval 2.45 to 2.97. Right? Any questions whatsoever about number 3? Everybody's good with this? So let's do number 4. I'm going to change one thing about number 4. I'm going to scribble this out. I'm going to change it from 50, and I'm just going to change this to 15. So instead of 50, I'm going to call it 15. And then again, take maybe 3 minutes or so for yourself. I'll give you guys a little bit less time now. Take about 3 minutes or so for yourself and see if you can answer number 4 by yourself with this change of changing 50 to 15. So that right there was 3 minutes. That's about as much time as you're going to have on the exam to do a problem like this, right? Just to give you guys an idea. Usually these problems are broken up into 2 questions, and then for 2 questions you get about 3 minutes for 2 questions combined, right? On the test, you get about 1.5 minutes per question. In this class, you get a little bit longer than that because here we have 90-minute classes. Usually I teach 75-minute classes during the semester or during the fall and the spring. But about 1.5 minutes, that's what you get per question. So let's do this problem. Well, as always, how do we know that this is a Chapter 7 question? Confidence intervals. Looking at confidence intervals. And whenever we're doing confidence intervals, how do we always start those problems? Awesome. Here, do we have a sample size greater than 30? Nope, I changed it to where it's only 15, so we're going to say no. And do we know our population standard deviation sigma? Nope, we only know our sample standard deviation, so we're going to answer no to this as well. So therefore, we're going to use what? T's. Awesome. So therefore, our formula that we're going to use is going to be x bar plus or minus t sub alpha divided by 2 times something divided by the square root of n. What are we putting up in our numerator? S. You guys good with this stuff so far? All right. Then we can start plugging in values. X bar, we said, is going to be 23.6 plus or minus. We'll skip t here for a second. S is going to be equal to 2.4, and n is going to be, I changed that to 15. So then we need to look up a t value. What are the 2 things that we need to know whenever we're looking up t values? Degrees of freedom. So degrees of freedom. And degrees of freedom so far is equal to? Good, because it's little n minus 1, so it's going to be 15 minus 1, which is going to be 14. What else do we need to know whenever we're looking up our t values? Our confidence level, good. In this problem, our confidence level is equal to 99%, which is equal to 1 minus alpha. So therefore, alpha is equal to 1%, and alpha divided by 2 is equal to 0.5%, or 0.005. All right, is everybody good with 0.005? All right, now if we take these 2 things and we take them to the t table, which is here somewhere, we're going to go to 0.005, which is going to be this column over here. And if we take this down now to 14 degrees of freedom, we're again going to be right here. Where these 2 things match up, we get 2.977. Everybody good with 2.977? We plug in 2.977 right here. If you do this arithmetic, you get 23.6. Oh, no you don't. You get 21.76 to 25.44. Right? You good with this? All right. Everybody else good with this as well? Then what's our last step? Interpretation. And we are 99% confident that the population mean mu is in the interval 21.76 to 25.44. Yeah. All right, it seems like everybody's good to go with these types of problems. Right? Everybody feel comfortable with these types of problems? Questions?
Where does the confidence interval come from in the beginning?
What do you mean? This?
It says 99% confidence.
Oh, where does the 99 come from?
Yeah, I know if it's like, I mean, large enough, but when you get to like 80% versus 85%, you decide if you're 80 or 85% confident.
Just to make sure that I'm understanding you right, you're saying, how are we picking these numbers? I'm just pulling them out of thin air.
In an actual.
And so in the actual real world, there's a couple different standards just depending on industry, right? If you look at like academic journals that publish stuff, there's a general rule out there where people usually want to be 95% confident. Another way of saying that is really we just restrict alpha, and alpha we usually just choose as being 0.05. In some academic journals, like in economics in particular, whenever you're publishing your results, you publish usually a set of 3 results. One where alpha is 1%, one where alpha is 5%, and one where alpha is 10%. But then again, that's very just industry specific, right? You don't want to just have 90% confidence whenever you're introducing like a new drug. So that's why in like medical journals and stuff, usually you have to be like at least 99% confident, and you usually have several trials that you run just to try to tighten up that confidence even more. But yeah, that's just dependent on industry. But in these examples, I'm just pulling those out of thin air. Yep, great question. Any other questions about any of this stuff? Yeah.
Is this like mostly like chapter 7?
This is all chapter 7 so far. Yep, chapter 7 is good. So in chapter 7, we're just going to do 2 more things in chapter 7. I'm sure you guys can figure out one of the things that we're going to do differently. What's one thing that we could do differently in these problems? Proportions, right? You think back to your interpretation, the only 3 things that we're ever swapping out in interpretation is a confidence level that Josh just asked about, but that's just coming out of thin air, right? That's just where we're setting up these problems. This thing that we're talking about down here for a confidence interval, well, one thing that we haven't changed at all yet, swapping out means for proportions. So now we're going to look at proportions. Now, if you look at the examples that we've done so far, whenever we're dealing with proportions, what's one thing that we're definitely not worried about? We're going to be interested in confidence interval. Right? We're going to eventually try to calculate out some interval. But if you think about this, suppose that this problem said proportions instead of means. And what would you not care about?
That's a good question.
I know you guys are probably sitting there going, yeah, I wouldn't care about all of this. Like, I'm forced to do this. Like, this sucks, right? I'd rather be at the pool or something. So yes, the standard deviation, that's a good answer. Not one that I was getting at, but that is a correct answer, right? That's a very good observation.
Would it be T?
No, we're still going to we're not going to necessarily use T's. So you're on the right track. So when would we not use T's?
Sample size.
Sample size, right? Let's think about that. Why do we not care about little n when we're dealing with proportions?
So it would be a large sample?
Good. So we don't look at little n whenever we're considering whether it's a large sample or not. And what do we have to look at to see if we're dealing with a large sample whenever we're dealing with proportions?
The interval?
The interval. Good. So now, one of the main differences that we're going to see, because the next step that we're going to do is we're going to start looking at proportions. One of the main differences for when we're dealing with proportions is we still want to figure out whether or not we have a large sample or a small sample. But for proportions, we don't care what little n is. We care whether or not that interval is between 0 and 1. Right? You guys remember that from when we were doing proportions in chapter 6? So let's take a look at the next page in our notes. The next page in our notes, we now start looking at population proportion. But one of the things that I want to start pointing out to you, and that's kind of where this discussion was going, is here we're dealing with large sample estimations for proportions. Yes?
Okay, before you move on.
Yes.
I don't know why I had it in my head that for the confidence interval, I was doing 0 to 1, like 0 to like 100%. Like if it was a negative number, it wouldn't be. If it was like over the percent, it would be. I don't know. So in this, I'm only writing, it's 90% confident, like what we're doing on this. I'm just figuring out the interval, right?
Okay.
I'm not deciding, am I deciding if it is in the interval?
No.
I'm just writing it out of the answer that I got.
That's right.
Okay.
Like, the only thing that we're trying to get at is we're just trying to get at the interval, right? Think about it like this. Let's take it to like a more intuitive example. Let's go back to that example where we were saying, hey, what's the average height of all students at UNC Charlotte? Are you ever going to really know what the average height is of all students at UNC Charlotte? No, you're not going to know, right? But one of the things that you can do is you can provide an estimate, and that estimate you can either give as 1 point, right, which is what we've been doing so far, but now in Chapter 7, we can start giving an interval. So what we can say is I can say, hey, tell me what the average height is of all students at UNC Charlotte, and you can be like 5 feet to 7 feet. I'm super confident that I know I'm not answering you incorrectly. But that's not really telling us a whole lot, right? So that's why what we're doing is we're always interested, our final answer is always just this interval, but we have no idea whether this interval is correct or not, right? Like, if you go back to that example, if I say, hey, give me an estimate for the average height of all students at UNCC, and you say, hey, it's 5'6.5" to 5'7", I'm gonna be like, damn, that's a good estimate, right? Like, you're giving me like a half of an inch estimate, right? But how confident are you then? Maybe not so confident. And what is that confidence level telling you? You cannot tell me whether or not mu is actually in there. It's just an estimate, right? Does that make sense?
Yeah.
So you're right that here our percentages are always going to be between 0% and 100%, right? But that's just expressing how confident we are in the interval that we're coming up.
Interval 0 to 1 for proportions.
Good, right? So now we're getting to this conversation. You're right. We're only going to use that interval from 0 to 1 for proportions. Because what we're saying here is this, right? That interval that we're using from 0 to 1, specifically this interval that we calculate out right here, we want this thing right here to always be between 0 and 1. Now, what does that mean? That means that, hey, if I start doing calculations for proportions, and I'm coming up with some number that's like negative 10%, well, I know for proportions that negative 10% just doesn't make sense, right? So therefore, what we're doing is we're calculating out a set of numbers, and if this set of numbers is giving us numbers that's reasonable for proportions between 0 and 1, now we're like, okay, cool, that's a big enough sample size. If the numbers that we have aren't giving us results that make sense for proportions, then what we're saying is that the reason why it's not happening is because our sample size is too small. Does that make sense? Cool. All right. So that's why whenever I said, hey, what's one thing that we're going to be doing differently now for confidence interval questions is, and you guys got really, really good at this routine because I always said, hey, how do we know this is a Chapter 7 question? You would say that it says confidence intervals. But then my next question always was, what's our next step? And our next step included the fact just to look at little n. But we know that whenever we're dealing with proportions, little n does not convey enough information to us. We want to know whether or not the numbers are between 0 and 1, and that's the big difference for whenever we're doing proportions. So, let's be a little bit more specific, right? So, whenever we start doing the next set of questions, one of the things I'm going to start asking you guys, just like I have before, is how do we know that this is a Chapter 7 question? To that, the answer doesn't change. It's always just that it says confidence intervals. But now that we're doing proportions, one of the things I'm going to start asking you guys next is, are we doing a confidence interval for a mean, or are we doing a confidence interval for a proportion? Right? So, how do we know that this is going to be a confidence interval question for proportion? Well, before we do that, why don't we go ahead and read the question so we're all on the same page, right? Number 1 says, to estimate the proportion of students at a large college who are female, a random sample of 120 students is selected. There are 69 female students in the sample. First, verify that the sample is large, then, if possible, construct a 90% confidence interval for the proportion of all students at the college who are female. Interpret your results. So, let's go through the process. How do we know that this is a Chapter 7 question? Well, all of us know now that we're doing some kind of confidence interval question. Now the second question that I'm going to start asking you guys is, how do we know, or are we dealing with means or proportions? Everybody's good at its proportions, right? Like it says proportions in the problem, so therefore we're dealing with proportions. Right? Is everybody good with that? If it says proportions, we're doing proportions. If it doesn't say proportions, we're not doing proportions. Right? Everybody good with that? Right? YMCA. Right? All right. Anyways, so here we're going to be doing proportions. Now, we're dealing with proportions. Now the question is going to become, right, our next step always was to find out if n is greater than 30 and if sigma is known. Right, that was always our next step. But now, because we're dealing with proportions, do we care what little n is?
Yeah.
We cannot simply look at this number and say that this is a large sample, right? We could easily have the numbers in such a way where little n is 120, but 120 is an insufficient sample size, right? It's just a small sample. Is everybody good with that concept? I tried to hammer that home when we were in Chapter 6. You guys see why we did so many problems like that now when we were in Chapter 6? All right. So here, what we need to do is we need to figure out whether or not our sample size is large. How do we figure out whether or not our sample size is large? Got to do that equation. All right, cool. Everybody's on the same page with that? All right. So we're going to do this equation. So is sample size large? Question mark. Well, let's try to figure that out. If we want to figure out whether or not our sample size is large, we're going to take p hat minus 3 times the square root of p hat times 1 minus p hat divided by little n, right, where the square root's over all that. And then p hat plus 3 times the square root of p hat times 1 minus p hat over little n. So we're going to try to answer this. Now, going back to your answer, Rachel, that you said earlier about sigma, and I said, yes, that's a very good observation. The reason why I said it was a really good observation is because technically we don't have sigma or s anywhere in this problem, right? Sigma or s is nowhere mentioned in this problem. However, also keep in mind here that technically this square root, everything in this square root right here, that is our standard deviation. And if you go back to Chapter 6, you'll see that that portion right there was written as sigma sub p hat. All right. So let's try to fill in this equation. The easy thing to put in here is little n. Right? So let me put in little n. We said that that was 120. But now the only other thing that we really need to know is p hat. And what does p hat stand for again? Not the population proportion. It's not the mean. No. I feel like you guys are like doing mental hangman up here. What could start with P? Sample proportion. Right? So P hat is the sample proportion. What's our symbol for the population proportion? It's not, oh my goodness. It's just P, right? P is for our population proportion, and P hat is for our sample proportion. All right. So we want to know what P hat is. P hat is our sample proportion. How do we figure out P hat? 69 people have a certain characteristic here. It's that they're female out of 120. So 69 divided by 120. And 69 over 120 is 0.575. So now I can just plug in 0.575 everywhere where I see p hat, which is pretty much everything that we still need for these equations. All right. Now we filled out this equation completely. Everybody good with where we're getting the values for this equation? Everybody's good with this? All right. Now, if we do this arithmetic, we end up with 0.440 to 0.710. 0.440 to 0.710. Now let me ask you, is this our confidence interval? No, this isn't our confidence interval. That's usually a source of confusion. People think that, I just created an interval, so this is my confidence interval. This is not our confidence interval. What does this interval tell us? Tells us whether it's a large sample or a small sample. Do we have a large or a small sample? Why is it large? Because it's between 0 and 1. Awesome. You guys are getting it. So here we have a large sample. All right. Now we have a large sample. So all that this has done, unfortunately, is just answer that first question that we were doing in the previous 4 examples, where I asked you, what is n is n greater than or equal to 30, right? In the previous questions, we could simply just answer that by looking at one number to determine whether or not we had a large or small sample size. But now we need to do this whole interval, and this interval is just answering that one question for us. Now here's an important thing. Obviously this takes a lot longer than just seeing whether or not little n is greater than or equal to 30. You only need to do this if the problem specifically asks you to verify that the sample is large. If the problem doesn't say, first verify that the sample is large, then you do not need to do this. You can assume that it is large, right? And you can go straight to like what we're about to do down here. Yeah, to the top up there. Yep. So you can skip all of this right here if the problem doesn't specifically ask you to do it. Right, is everybody good with that? Otherwise, if you come across proportion questions, they're going to take you more than a minute and a half to do, and then it's just going to bog you down, right? So you don't have to do this unless it specifically asks you to do that. Everybody good with that? All right. Jay, you got a question?
I answered it.
Good. All right. Everybody good with what we have up here so far? All right. Now here's the important thing. Let's go to our formula sheet. Where are we now on this formula sheet? Like right below what we were using before, right? Inference about a single, just one, population proportion. So the only formula that we have then, when we're dealing with population proportions, single population proportions, is just this one right here that I've circled a couple of times. Some of you are going, sweet, right? There's just one more formula. In this formula, do we have Z or T? Z. We only have Z. We never use T. Right? Is everybody good with that? So, let's think back now to those 2 questions that we've always asked ourselves in previous questions. Is n greater than or equal to 30? We just determined that we don't use that anymore. And is sigma known? We don't really have a symbol for sigma anymore. So the only thing that we're really ever doing is determining whether or not we have a large or a small sample size. If we have a large sample size, do we ever use T? No. If we have a large sample size, the only thing we ever use is always just Z. The only way that we can ever get to T is if we have a small sample size. So we never use T, so therefore what's going to happen if you have a problem that has a small sample size in it? You can't move forward, right? You can't do it, right? So here's an important consideration. We're going to check, if you have to, we're going to check to see whether or not we have a large sample size. if you have a large sample size, you're going to use this formula right here. If you do not have a large sample size, the answer to all of those questions is cannot be determined. Right? So everybody good with that? All right. So if we have a large sample size, then we can use this formula. If we do not have a large sample size, then you simply just have to stop. You can't do it. Right? Think about it like this. Suppose you went out and you took a sample, and your sample was really small. And you started to calculate out this interval now. And this interval started giving you numbers for proportions that were like negative percentages or percentages above 100 that we know just don't make sense. Well, if your sample is giving you this information, it's completely pointless to try to come up with an interval because you're already just working with numbers that don't make sense. Right? Is everybody good with that? So therefore, if we're getting numbers that don't make sense, we can't use it. The only fix to that is to go out and take a larger sample. But in this class, we don't deal with sampling. We always just say, hey, we have a random sample. We never discuss how to actually sample stuff in this class because it's just outside the scope of this class. Right? So that's a long-winded explanation for saying the only way that we can ever use this formula is if this is between 0 and 1. If you don't have to verify that it's between 0 and 1, we always just jump straight to this. So here we found out that it was between 0 and 1. So now we can calculate out our confidence interval, and our confidence interval formula, as we have up here, but we also had in our formula sheet, is p hat plus or minus z sub alpha divided by 2 times the square root of p hat times 1 minus p hat over little n. All right, so let's just stop and take a gander at this formula here for a second. Everybody should feel really confident now about figuring out p hat. Right? We figured out p hat from before. It's just 69 over 120. Right? This is sample proportion. The only other thing that we need to put into this formula then is little n, but we should then know what little n is because we're using that to find out what p hat is. Then the only other thing that we still need is z sub alpha divided by 2, which we've now done at least a dozen or 2 times. Right? So if you just look at this formula, there's really nothing that's really happening new in this formula whatsoever. Right? If we plug in the values that we've gotten so far, we're going to have 0.575 plus or minus, I'll skip z again, 0.575. I'm not going to write 1 minus 0.575 because I'm running out of room, but 1 minus 0.575 is simply just 0.425. So I'm just going to write 0.425 right here, divided by 0.575. Everybody good with this so far? Oh, thanks. Mess that up. Gosh, don't tell my boss. Oh, it's on video. Oh, gosh. All right. Set stage for eternity. All right. The only thing that we still need to figure out then is what our z value is. What's our confidence level for this problem? 90, what is it? 90%. Then alpha is how big? Alpha divided by 2 is? And then what's the z value that corresponds to 0.05? I'll answer that question in just a second. That's a great question. What's our z value? Good. 1.64 or 1.645. So now let me talk about that one more time again. Do we have a column in this table that corresponds to 0.05? Yes. It's this column right here. If you follow this column all the way down to the very, very last row on the back side, you get 1.645. So the answer choices, I know I said this earlier, but I'm going to reiterate it again. The answer choices that you're going to start to see now is going to use this z value to a third decimal place. So 1.645. So again, you can use 1.64, and you could use 1.65. The answer choices that you're going to get for those are just slightly off, because the answer choices that we're going to now see are going to be made using the numbers of 1.645. Betsy, does that answer your question? Good. Awesome. So we're going to use 1.645. If you calculate out this interval, now we're going to be between 0.501 and 0.649. So now I know I'm carrying 3 decimal places. I'm not just carrying 2 decimal places or 1 anymore. Again, your answer choices are never going to be that close, but try to carry decimal places. Now, is this our confidence interval?
Yes.
This is our confidence interval, right? So now we're done with our confidence interval. What do we still have to do for this problem then? Interpret our results. And what is our interpretation? No, you had it right, that the population, because that part is still there, right? That part was never in a box.
Proportion.
Now it's proportion. Population proportion. What's the symbol for population proportion? P is in the interval, what we just calculated out, 0.501 to 0.649. So we're always estimating something about the population. Now we're estimating out the proportion P. And then again, the other things that we swap out is our confidence level and the interval that we're doing. All right, how do you guys feel about this? So I usually don't do a whole lot of examples for proportions. But I think you guys are recognizing why we don't need to do a whole bunch of examples for proportions, right? Because the only thing that we're really swapping out is how we check to see whether or not we have a large sample size. But we've done that before numerous times. And then whenever we're doing confidence intervals, the only formula that we have is this one right here, and we can only do it if we have a large sample size. But what we're plugging into this formula is stuff that we've already used numerous times before. All right. Are there any questions about proportions?
And you said, like, if it's a small sample, we don't have to worry about that.
Exactly. If you get to this point right here and you say, nope, it's small, then you simply just stop. Yep.
So if it's a large population, p hat equals p, but if it's a small population, p hat is like the sample divided by the total number of people. It's like the female divided by the sample itself.
So whenever we're calculating out p hat, our sample proportion, we're always going to take a group that has a certain characteristic and divide it by the total number of things that have that characteristic, right, in our sample. No, I'm sorry. I said that completely wrong. We're going to take the total number of people in our sample, right? So remember, like, our population is the whole big thing that we're sampling from. Our sample is just some subset of that sample. But inside our sample, we're going to have certain things that have a characteristic. I'll make those in dark. And then we're going to have certain things that don't have a characteristic. So whenever we're trying to calculate out p hat, we're going to take the number of things that have that characteristic and divide it by our sample size. We're not really concerned about our population size. Technically, we have a requirement here that if we don't know what our population distribution is, that we have to have a large population. That's outside the scope of this class. It's just a technical little mention. All right, so the only thing that we haven't covered then in Chapter 7 is just this page that deals with sample size. The only thing that we're really going to mention then is we're saying this. What we've done so far is we said, hey, tell me an interval estimate for something, right? But now what we're going to kind of do is kind of what Josh was asking about earlier. Well, in the real world, what is our confidence level? Where are these confidence levels coming from? generally speaking, there's a confidence level, right? The most frequently used one is a confidence level of 95%. So what people say to you is, tell me the average height of all students at UNC Charlotte and give me an interval that you're 95% confident in, right? That's a reasonable assumption or reasonable ask to make. But now if you want to have a certain level of confidence in an interval, what you're saying is that you have to have a sample size that matches that confidence level. So if somebody comes to you and says, give me an interval, but don't just give me any interval, give me an interval that you're 95% confident in. Now, if you want to have a certain level of confidence, now you can go and take a certain sample size. What we're kind of doing is we're kind of working backwards. So what we're going to do at the beginning of Monday's class is we're going to look at sample size considerations. Your homework, I think there's only like maybe 4 questions or so in there that says determine the sample size. Those you won't be able to do yet, right? Or if you want to try to figure it out with this stuff right here by yourself, you can try to figure it out. But we're going to cover this on Monday's class. You can do like 90% of your homework. The only questions that you can't do that say determine the sample size.
The test is what chapters?
The test is going to be, it seems like it's just going to be on chapter 7, and it's going to be on Wednesday.
Okay.
Yep. All right. I will see you guys on Monday. Have a great weekend.